Hi, my name is Kayırbek Buksukbayev and I am a chemistry teacher at NIS Kızılorda. Today we are going to study chemical equilibrium. Good morning, students. Okay, you can have a seat. Today we are going to study equilibrium, and these are the learning objectives. Our learning objectives are to recall and be able to use ideas from previous teaching on equilibria, including the concept of dynamic equilibrium. Be able to predict the effects change of temperature, concentration and pressure on the equilibria, and be able to write the equilibrium constant Kc for a given reaction. What is equilibrium?
Equilibrium is a balance. For example, if we have the same number of girls and boys in our group, we can say that we have a balance between girls and boys.
Very nice. So, what is a chemical equilibrium? And can we see a balance in there? To explain that, let me write two types of reactions. The first one is irreversible reaction. Another type is reversible reaction. So let's have a look at these reactions. What is reversible reaction?
This is a reaction that goes to completion.
Very nice. Any other ideas?
It's when the reaction proceeds only in one direction.
Very good. Okay. Let's write down the reaction. For example, a substance A produces substance B, and the reaction goes to completion. But the substance B does not change to the substance A. So the backward reaction is impossible. This reaction is irreversible reaction. Let's do the simple reaction. Okay. First of all, let's take some magnesium powder and pour it into a test tube. Magnesium is a very active metal, so we have to be very careful while doing this reaction. I'm going to use hydrochloric acid, which is very dangerous acid. Let me pour some drops of hydrochloric acid. As you can see, it produces gas. It is a hydrogen gas. If we touch the test tube, we can feel that the temperature has increased. And after a while, the reaction is slowing down. As you can see, the reaction has completed. How can you prove that the reaction has completed?
Because it doesn't produce bubbles anymore.
And thus, hydrogen gas reacts with aqueous magnesium chloride. Let me write down the reaction. Can anybody answer this question?
No, it doesn't, because magnesium is more active than hydrogen.
Excellent. Another example is the reaction between sodium hydroxide with hydrochloric acid. And it's a very dangerous reaction, and you have to be very, very careful while doing this process. Let's do this reaction now. Okay, now we're going to use again aqueous hydrochloric acid. Let me pour some drops of hydrochloric acid into the test tube. And then add with a pipette a couple of drops of sodium hydroxide solution. here you do not observe any change. But after a while, you see that the temperature has increased and it turns to sodium chloride and water molecule. In order to check that the reaction has completed, let me check the acidity and basicity of hydrogen chloride and sodium hydroxide. As you know, hydrogen chloride is a strong acid, and it should turn the litmus paper, the yellow litmus paper, into red. Let's drop some hydrochloric acid into an indicator, and you see the very dark purple color of the indicator. And if we do another test with the sodium hydroxide solution, let me add some sodium hydroxide into yellow indicator. You can see the color change. And our indicator turns to dark blue, purple color. It shows that the pH is greater than 7. Now, after the reaction has completed, can we say that the sodium chloride reacts with water molecule? Okay, now if we add sodium chloride aqueous solution to water, can we get sodium hydroxide and hydrochloric acid? Of course not. And how can we check that?
If you put the yellow indicator into the tube, it neither changes blue or red.
Very nice. Okay, let's do that reaction. Let me take some sodium chloride and add some water. Let me mix this two solutions and look if we get sodium hydroxide, the strong base, and hydrochloric acid, very strong acid. How can we check that? You mentioned before that we can check it with universal indicator, and it should turn blue or red in color. Let me get some of these mixed solutions and pour it into a yellow indicator. Does the indicator change in color?
No.
No, of course not. So it means that we couldn't produce sodium hydroxide and hydrochloric acid. Okay, can you give any other examples?
If we burn hydrocarbon, for example a butane, it will produce water and carbon dioxide gas, but it won't go backward reaction and it won't react to get butane and oxygen.
Very nice. Okay, we have learned the irreversible reactions. Now, let's have a look to the reversible reactions. Reversible reactions occur when a substance A changes to B and the substance B can produce A. This is called reversible reaction. What can you say about reversible reactions?
It doesn't go to completion.
Very nice. Any other ideas?
So the reaction produce it both in forward direction and backward direction.
Very good. Let's do another reaction. For the next reaction, I need some hydrated copper sulfate As you can see, the hydrated copper sulfate is blue in color. And I'm going to heat it up while the change occurs here. I'm going to heat it up until something changes with the hydrated copper sulfate. Has 5 moles of water molecules. And when we heat it up, the water molecules disappears and leaves the copper sulfate alone. And you can see the change, that the copper sulfate is becoming white in color. The blue color disappears. Let me mix the copper sulfate for the reaction to go faster. Okay, it has totally changed into a white color. Okay, now let's have a look. What happened to the hydrated copper sulfate? Okay, what can you see?
The blue color of hydrated copper to sulfate changes to white.
Very nice. Okay, and if we add some water to copper sulfate, anhydrous copper sulfate, it will immediately change to blue in color, and it will produce hydrated copper sulfate solution. Okay, let me do this reaction. Let me take some couple of drops of potassium thiocyanate. Pour it into a beaker. Then add some iron 3 chloride solution. As you can see, the color changed into red. Let me add some water. And divide it into 3 test tubes. First test tube, second one, third one. I won't mix anything to the first test tube, but I'm going to add some iron potassium chloride to the second solution. As you can see, the color changed. If you compare these 2 test tubes, the first test tube is more dark red in color, and the second one is less dark. And let me add some iron 3 chloride into the third, no, okay, into the third test tube. As I add more iron 3 chloride into this test tube, the color gets darker. If we compare the first and the third test tube, and the third test tube, the color is brownish in color. So let's compare these three test tubes. The first one is dark red. The second one is less dark, and the third one is brownish in color. Okay, what's happening in this reaction? When I add potassium chloride into this reaction, the concentration of potassium chloride increases and it shifts the equilibrium to the side of the reactants. And the color will change because the concentration of the iron thiocyanate increases. And what happens when I add iron 3 chloride into this mixture? When iron 3 chloride mixture is added, the concentration of this solution increases, and as a result, the equilibrium shifts to the side of products. And as a result, we have more iron thiocyanate. That's why the color gets darker. Another example. If we mix nitrogen with a hydrogen gas, what can we produce?
An ammonia gas.
Very nice. In this reaction, the reactants are not used completely. Some products are formed, but the maximum theoretical yield is not obtained. A mixture of products and reactants is formed. The products react together to reform reactants at the same time as the reactants are forming products. This type of reversible reaction is called an equilibrium reaction. We show that equilibrium reactions are reversible by the sign of two arrows in opposite direction. In the reaction of producing ammonia, molecules of ammonia are breaking down to hydrogen and nitrogen at the same rate as hydrogen and nitrogen molecules are reacting together to form ammonia. An equilibrium reaction has four particular features at constant conditions. The first thing is it is dynamic. The second characteristic is that the rate of the forward reaction is the same as the rate of the backward reaction. And the third characteristic is that at equilibrium, the concentration of the reactants are constant and the concentrations of the products are also constant. And it means that it will not change. So, the fourth feature is that the equilibrium reactions occur only in a closed system. Okay. These are the four features of the equilibrium reactions. So, let's have a look for the first characteristics. Dynamic. What can we understand by the term dynamic? It means that the reaction is continuously being perceived. So the forward reaction happens at the same time when the backward reaction also happens. It means that the reaction is dynamic. The rate of the forward and backward reactions are the same. It means because of the rate of the forward and backward reactions are the same, the equilibrium establishes, And we may not observe any change during this reaction because the rates are the same, and that's why the concentrations are also do not change. The third feature here, when the products and reactants are in constant concentration, we say that the equilibrium is established. So, students, now let's write down in pairs how can you explain that the concentration of the products and reactants are constant. For example, let's take a reaction of hydrogen with iodine gas, which produces hydrogen iodide. We can start by using a mixture of colorless hydrogen gas and purple iodine vapor, or using only colorless hydrogen iodide gas. So, let's write down on your papers. If we take 5 mole of hydrogen molecules and 5 mole of iodine molecules at 500 Kelvin temperature in a vessel of volume 1 cubic decimeters. As time passes, the purple color of the iodine vapor fades until equilibrium is reached. Let's state that equilibrium is established and the amount of iodine is 0.68 moles. The amount of hydrogen is also 0.68 moles, and the amount of hydrogen iodide is 8.64 moles. I want you to draw the graph of the concentration that changes as time passes, starting with the first reaction. I give you 4 minutes in order to draw this graph. What is this?
This is the line
Okay, and the concentration of
both hydrogen and
Okay.
iodine.
So in your graph, this is the line of the hydrogen iodide, which starts from which point? Where does it start from?
0.
0. But you don't show that it starts from 0. Why it should start from 0?
Because at the beginning of the reaction there wasn't any hydrogen ion.
Very nice, because we have only the reactants at the beginning of the reaction. What is the unit of the concentration? Mole per cubic decimeters. In order to explain this, let's come to the blackboard and show your work. Can you explain to the class what's happening in this graph?
The concentration of reactants will decrease into
At this point, and What happens next?
And it will be the constant at the equilibrium.
Very nice.
And concentration of hydrogen iodine starts with 0 and increases and will be constant at the equilibrium.
Very nice. And then it will remain unchanged. Very nice. Thank you. Now let's see what the equilibrium constant is. For an equilibrium reaction of the form A plus B produce C plus D, the equilibrium constant is equal to the concentration of C to the power of coefficient of C multiplied by the concentration of D to the power of the coefficient of D divided by the concentration of A to the power of the coefficient of A multiplied by the concentration of B to the power of the coefficient of B. So this Kc is shown as the equilibrium constant. Now we are going to look at the Le Chatelier's principle. So it says, when a change is applied to a system in dynamic equilibrium, the system reacts in such a way as to oppose the effect of the change. For example, a rose bush grows with increased vigor after it has been pruned. A chemistry example. If you do something to a reaction that is in state of equilibrium, the equilibrium position will change to oppose what you have just done. Now, let's look at the factors that affect the position of equilibrium. The concentration changes the equilibrium constant. To maintain that constant, the composition of the equilibrium mixture changes. If you increase the concentration of a substance, the value of Kc will theoretically be affected, as it must remain constant at a particular temperature. The concentrations of the other species change to keep the constant the same. When studying the effect of change in pressure, we consider the number of gaseous molecules only. The more particles you have in a given volume, the greater the pressure they exert. If you apply greater pressure, they will become more crowded. However, if the system can change, it will move to the side with fewer gaseous molecules. It is less crowded. Temperature is the only thing that can change the value of the equilibrium constant. Altering the temperature affects the rate of both backward and forward reactions. It alters the rates to different extents. The equilibrium thus moves, producing a new equilibrium constant, and the direction of movement depends on the sign of the enthalpy change. Catalysts work by providing an alternative reaction pathway involving a lower activation energy. When we say about the catalyst, we shouldn't say that the catalyst decreases the activation energy, but the catalyst finds another alternative way that has a lower enthalpy than the original reaction has. So the reaction mechanism changes, and those steps has lower enthalpies, activation energies. If we look at this Maxwell-Boltzmann distribution of molecular energy, we can see in the graph that when we add a catalyst, the molecules that has more energy than the activation energy has increased, and thus the rate of reaction increases. And if we see at the second graph, the activation energy of the original substance is more than the activation energy when the catalyst added. So the less energy used, the more efficient production we have. Now students, let's write down the homework in our chemistry course book, page 149 and 150, questions 1, 2 and 3. Okay, the lesson is over. Goodbye.